Right.
Okay, well, we're very happy. Oops, sorry, I have to press continue here. Yeah, we're very happy to have Djuna Croon from Triumph, and is going to tell us about new physics and the black hole mass gap.
Yeah, thanks for having me. Yeah, so it's a shame I can't visit in person, but you know, I'm gonna try and make it as exciting virtually. So please, if you have any questions at any point, just stop me. I think that's like the best way to make it feel like as kind of lifelike as possible. So you know, please interrupt. Um, yeah, I'm going to talk about a few projects that I've done over the summer with some collaborators that I have been very excited about. And yeah, it's kind of a continuing research program, really. You know, this is kind of not the end of the story yet. And, you know, a lot of these understandings like that we have of the black hole mass gaps are still kind of in flux. And as a result, you know, not everything I'm going to tell you is set in stone, and it's kind of a developing understanding that I'm presenting. But I'm very excited about it, and I see it as like offering like quite a few opportunities for particle physics. Right, so let me just start off with this kind of event that happened in September. So this discovery that was announced, GW 190521, which was announced and also subsequently drew quite a lot of press. I've sort of collected a few of these here. You'll notice that this middle one is in Dutch. I couldn't resist because I'm Dutch. And also, I'm featured in this article, so that's why it's there. But like a lot of, very major news publications, science news, but also kind of general, like the New York Times, wrote about this particular event. And what was written about them is that they were the impossible black holes, which I quite liked. And that's kind of like what this talk relates to as well. So why were they impossible? So this is from the announcement paper by the LIGO and Virgo collaboration. And what you see here is on the x-axis, the primary mass. It's kind of by definition the largest black hole mass in the merger. And then on the y-axis, the secondary mass. And then this gives the posterior for the best fits of these masses in the merger. And you see that these are actually very large things, very heavy things. So the best fit sits somewhere around like 80 solar masses for this primary component and like somewhere about 65 or higher for the secondary component. So why is that so strange, these very large masses? Why does that mean that these are the impossible black holes? Well, to understand that, I'll just wind back a little bit to the story as it started to unravel for me, at least a few months before this discovery, early in the summer, as I learned more about this kind of phenomenon. Okay, so this is like the situation as it was then. So these are the binary mergers that LIGO and Virgo observed in their first two observation runs. So as you might know, just in terms of timelines, they have already concluded their third observation runs. And earlier this month, this is actually, I think 2 weeks ago, they shared the data of the first half of the third observation run. But this is the way it looked before that announcement, before like this month and early this summer. The data from the first two observation runs included lots of like light things, then black holes, that were very heavy, and that merged to form even heavier stuff. So just sort of noticing on this plot, you see here on the y-axis the masses in solar mass, and then on the x-axis is just random. So what you can already kind of immediately notice is two things. So here at these lower masses from 2 and a bit solar masses up until about 5 solar masses, there is this mass gap that you probably already knew about. It's just between the heaviest neutron star that's been observed and the lightest black hole that you can form. And this is kind of, this is what people refer to as the mass gap. And even LIGO and Virgo label, in their, in GRACE, which is their database of gravitational wave events, they label events as mass gap if they have a component star which lies, somewhere in this range.
Sorry, can I ask a question already?
Yeah, absolutely.
So all those dots that are not mergers, does that mean that they can observe black holes that don't merge?
Yeah, so
What
these are
those?
so these are actually not observed by LIGO and Virgo. These are just neutron stars that have been observed via electromagnetism, via like their
Oh, okay.
optical. Yeah.
Okay.
So they're in here, I guess, just to guide the eye, because like LIGO and
Right.
Virgo in their first 2 observation runs only
Okay.
observed 2 of these mergers.
Okay.
Yeah, so that's correct. So in principle, LIGO and Virgo can only observe merging things because they have a changing quadrupole moment, which leads to gravitational wave emission.
Right.
So in principle, like other supernova explosions might give us a gravitational wave signal as well, but that is not in this plot.
Okay, thanks.
So so that's this mass gap here. Earlier, like in the summer, I think it was in July, around the same time as the xenon excess was reported, there was an interesting event which had a progenitor inside this mass gap, 2.6 solar masses, which also is kind of a difficult thing to explain. It could either be a very light black hole or a very heavy neutron star or something else entirely. So this lower mass gap has already been the topic of scientific exploration, and particle physicists have looked into this as well, and people have studied this in the context of primordial black holes, for example. But what I am going to talk about today is this other mass gap that you perhaps know less about, and that is a mass gap which we can refer to as the upper mass gap, and it extends from about 45 to 50 solar masses of black holes up until, say around about 100 solar masses. So that's a mass gap in which you wouldn't expect, astrophysically speaking, you wouldn't expect black holes to form in supernova explosions. So I'm going to explain to you why we think that is there first. So first, this whole picture is often referred to as the stellar graveyards. I'm going to give you a sneak peek of what this looks like with the first half of the O3 data. That's this. So you see that you kind of can identify again, maybe more or less a mass gap again. So these are kind of the best fit masses. LIGO and Virgo can't exactly measure the masses of black holes, so these will have error bars in any realistic kind of plots. But let me just sort of talk about like the stellar graveyards and what actually populates it. So typically in the LIGO and Virgo mass range, there's black holes, and they are remnants of very, very heavy, low metallicity early stars, so population 3 stars. So these are low metallicity. What that means is that if you sort of look at the mass fractions, they are primarily made of hydrogen and helium. So any heavier kind of element exists less in this star in a very small mass fraction. And these are hypothetical objects, but they would have existed at high redshift. So a good high redshift telescope would be able to observe these things directly. And they would have masses, between 20 and 130 solar masses. These are like pretty heavy things. So they haven't been observed directly yet, but they're a target for example, the James Webb telescope. So these would have lived for some time, but they would have eventually have burned through all of their hydrogen and their helium and have gone through stages of heavier element burning, and eventually would have burned out of their fuel, and they would have undergone a supernova explosion, and the core would have collapsed. So let's study how that works. And I'm going to sort of start the evolution from the 0H helium branch, which is when at the end of hydrogen burning, the star primarily is composed of helium. So that's here in this plane. You can see here on the y-axis, I have the core temperature in Kelvin, because I'm using astrophysicist units now. And here on the x-axis, I have the core density in gram per centimeter cubed. So this is really, CGS astrophysical units that I've adopted. And I'm studying the evolution of 3 different stars that I'm putting in with a stellar evolution code called MISA. So this is the latest evolution, the latest version of a well-used and well-documented stellar evolution codes. So I'm initializing these stars here at the start of helium ignition. So, and then I'm evolving them as they evolve through this plane, and their core temperature and core densities go up. So the stars that I'm putting in are one that is 120 solar masses, one that's 40 solar masses, and one that's 70 solar masses. So what's happening like as I do that? So what happens during helium burning is mainly two nuclear reactions that fuel the star and ensure that it's stable against gravitational collapse. So the first one is this reaction here in the top, which is often referred to as triple alpha, because there are three of these like helium atoms. First, like these helium atoms fuse into beryllium and then capture another helium to form a carbon atom. So this releases some energy. And then what may further happen is this carbon atom captures another helium alpha particle and forms oxygen. So this is referred to as like 12C16O. So these two nuclear reactions are important during helium burning, and they ensure that the star is fueled, if you will. Now, at some point, the star will have burned out of all of their helium, out of its helium, and that's when helium depletion happens, and the core will start to collapse again, and at some point become hot enough to start to burn carbon. So that's when all these reactions happen. These are not so important for what I'm going to talk about today, but something we've also looked into, on the site, and you can ask me about if you want. Okay, so this by itself wouldn't be so interesting if it wasn't for this other region in this plane here, which I've dashed here with a contour, in which the star is unstable. So why is that? Well, if you're attentive, like what you might have noticed is these core temperatures are very, very hot, much hotter than other astrophysical environments that you may know about, like much hotter than the sun, for example, hotter than like the tip of the red giant branch, etc. And they are so hot actually that you come near the mass of an electron. So if you do a quick calculation, the mass of an electron is about 10 to the 10 Kelvin. So you're kind of near that already. And so what can happen around these temperatures is that in the tail of the Boltzmann distribution, you may start to produce electron-positron pairs. So that's important because the stars that I'm talking about are supported by radiation pressure. So they have a sort of an adiabatic parameter, which is 4/3. But in the tail of the Boltzmann distribution, these electron-positron pairs are created, and they're non-relativistic when they're created. And therefore, they soften the equation of state, and they render the star unstable. So why is this region shaped like it is? It's shaped like it is because here at the top of this, at the ceiling of this region, the electrons are actually primarily produced relativistically, and therefore actually don't soften the equation of state, but actually support it. Here on the right, the star is supported by something else, ionic pressure. And here in the bottom of this region, the process that produces these electron-positron pairs is too suppressed to be important. So here's that region in the plane again, and you see that it is mostly important for these larger stars, which are like slightly hotter per density, if you will. So this is the region in which electron-positron pairs soften the equation of state. Okay, so what happens then if you get this pair production? Well, that's actually interesting. So I borrowed this diagram from this paper, by a bunch of astrophysicists that have like sort of applied knowledge that has existed for a while now. So I have like my massive helium core. So imagine now I'm starting to pair produce electron-positron pairs. What happens is they soften the equation of state and they trigger a collapse, a core collapse of the star. Now, because during helium burning, I actually made oxygen. So oxygen, as it turns out, like when you heat up the core, this oxygen in the core might explode very violently. So the core becomes hot enough to ignite oxygen. Then three things may happen. And what happens depends on quite how massive the star is. For a very, very massive star, so like I'm saying here, about 200 solar masses going in, you actually kind of shortcut the whole process and you get like this other kind of photodisintegration instability, which triggers direct black hole collapse. But if you have a slightly less heavy star going in, then what might happen is the ignition of oxygen is so leads to such a violent explosion that you actually unbind all of the material in the star, and so you wind up with nothing at all. So that you have no remnant at the end. So that's what's called a pair instability supernova. If you have a slightly less massive star, what might happen is, so you ignite oxygen, the explosion is violent, but not quite violent enough to actually unbind all of the material, which leads to, you have sort of still bound material left, and then you undergo cooling, but at some point you pair produce again, and you might go through the cycle a few times, losing some of the mass at this step every time, and eventually cool down, settle into thermonuclear, stable equilibrium again, and eventually undergo core collapse and form a black hole. So that's what's called a pulsation pair instability supernova. Right, and this is kind of what a picture looks like, and this is still, just to assure you, the completely standard model. This only relies on the fact that electron positrons have a particular mass. This is kind of like the type of picture that you might see. So here on the x-axis, I have the mass of the star that I started off with. So the mass at helium, the 0H helium branch. Then here I'm showing various masses. So this line is just y equals x. This is just kind of like the line of the initialized star, basically, the mass of the initialized star. Now, there is kind of something called stellar winds. So the outer shells of this ball of hydrogen and helium is less strongly bound, and typically you lose mass during stellar winds. So there's a well-described procedure to go from this mass going in to the mass at helium depletion. So that's what this line is. And you see that in our simulations, we find that the masses like the lighter black holes, or the lighter stars going in, form black holes eventually that are more or less equal to the mass of the star at helium depletion. But as I follow this to the right, instead what happens is that the black holes that I end up with are lighter than the mass of the star at helium depletion. And what's happening here is that the star is shedding mass in these pulsations. And if I follow this line all the way to the right, what I find is at some point I'm not finding a remnant at all. And that is when the oxygen explosion was so violent that all of the material in the star was unbound. And I end up with no remnant at all. So, okay, so a direct implication of this is what you can read off, like just sort of following the top of this curve to the y-axis, is that there is a maximum mass of the black hole that I'm ending up with these input stars. And here you see that's like around about maybe 45 solar masses. So I should say this, what I'm showing you here, like I have a metallicity that I've assumed it's about, it's a tenth of the solar metallicity, which is a little bit high for these stars. So later I'm going to relax this assumption a little bit. I'm going to take lower metallicity, which will push this up a little bit higher.
Could I ask a question here? So
yeah.
So it seems like for this gap is originating from this region where you're getting this explosions. Yes, that I follow that. So it's a famous thing that in ordinary supernova, people have a hard time understanding the actual explosion, right?
Mm-hmm.
Is there some reason why this is thought to be under better theoretical control, this particular type of explosion?
Yeah, it's a good question. So, okay, one thing I should say is that what I'm modeling here, so MESA is like a 1D stellar evolution code. It assumes radial symmetry. So it's like we are not modeling the supernova explosion at the end. What we're doing is like we're figuring out how much of the material at the end of the simulation has like a velocity less than the escape velocity. So it's gravitationally bound to the star. And then we assume that that material is not blown out in the supernova explosion. The pulsations, though, it's a completely different mechanism. So the mass that is lost in the pulsations is you can track that with the stellar evolution codes. And so, but if you would have a model, if you would have some reason to think that more mass is lost in the supernova explosion, then you can consider this kind of a conservative estimate for the edge of the mass gap, if you will.
Maybe can you go back to the previous slide? I mean, maybe I might not be understanding
Yeah.
this very well, but so from this slide here, I got the impression that that the gap was because the heavier masses underwent this explosion, this thing that you have, the big explosion,
Yeah.
rare instability supernova.
Yeah.
And so if that somehow didn't happen, then
Mhm.
your story would be completely different. But
That's right.
you're somehow, sounds like you're telling me that you're not, sounds like you were trying to say that you're not very sensitive to this. So I think I'm not still not understanding something.
Yeah, I mean, I'm gonna go into it in a little bit more detail. I'll show you some other sort of plots as well later. But what is happening is that what is happening is that there's this softening of the equation of states, which means that the star will contract and it eventually have a temperature that is hot enough to ignite oxygen burning. And we understand oxygen burning quite well. So we know how much energy is released then, and we can sort of simulate like that kind of process, and then track like how much sort of energy the stuff in the star gets, and that it's like gravitationally unbound to the star. It's different from like sort of supernova explosions at the very end of this like whole cycle.
Oh, okay.
Because it's just kind of triggered by like prematurely collapsing, like before you've burned through the star, and then having kind of like a core which then is violently burning like an element, in this case oxygen. So
Okay.
yeah.
I think I got the impression. Why don't you go on and I'll.
Okay. Yeah,
Thank
absolutely.
you.
Yeah,
Appreciate
absolutely.
it.
Okay. So okay, then you might ask, okay, well, I mean, this is astrophysics and stellar, there's a lot of uncertainty about physics in stellar cores. And absolutely, that's also kind of something that like my impression was going into this project. So in particular, in this case, there's astrophysical uncertainties, there's nuclear uncertainties, and there's numerical uncertainties that relate to doing this type of situation. So astrophysicists have like considered this process much longer than we have. And they have actually kind of mapped out what type of uncertainties exist and how much of a role they play. And this is from a paper from late last year by a few of the astrophysicists we've been talking to, and that have been sort of involved in studying this. And what you see is that most of these uncertainties, especially to do with numerics, for example, but also uncertainties to do with that are physical, to do with like weak scale physics, for example. This is to do with like cooling and for example, are they are there, and they're undeniably change kind of the edge of the mass gap that you would predict by a few solar masses, but not by too much more than that. The only thing that really stands out is the uncertainty here on the nuclear rates. So it says rates, these are the nuclear rates. And in particular, what's very important is this rate of creating oxygen during helium burning. And I guess that makes a lot of sense, right? Because it is oxygen that gives rise to this kind of explosive pulsation. And if you produce less oxygen during helium burning, then that's just like less important of a reaction. But then luckily, as it turns out, so this was using a nuclear rate. So this is kind of this nuclear rate, I should say, is a target for nuclear physicists generally, because it's important generally in kind of astrophysical environments. And hence there's been a lot of work on this rate. And what's sort of the code that was used sort of to study this, what it used is like a Starlip rate, which was from the early 2000s, but there have been updates to that. And in particular, same people, or kind of like an overlapping set of people, redid this analysis early this year. And what they're finding with this new rate by James de Boer et al. Is that like the uncertainty due to nuclear rates is much smaller than was initially thought. And we redid that as well, and we find something consistent. We actually find like a central value that is shifted by 1, and then error bars that are also both shifted by 1. But yeah, so this rate is still the most important, but this uncertainty is still the most important. But the uncertainty is really kind of you should think of like about for, a few solar masses, and not like, not like 20 or something, not 15. So, okay, so given all that, so I've told you that like we predict a mass gap of around about 45 to 50 solar masses with these uncertainties. But now you might say, okay, but I started this whole talk talking about this GW 190521, and there we found a black hole with 80 solar masses and another one with about 65. So how is that possible? Okay, so now I'm going to talk about like how we came into this story. So we, started working on this early this year. I would say late spring this year. That's when I kind of started to learn about, pulsation pair instability, supernova, and I was wondering how they would be affected by new physics. And I started talking to Sam McDermott, who's a postdoc at Fermilab, and Jeremy Sackstein, who is faculty at Hawaii, to sort of see what we could do to study that. And later on, we were joined also with Eric Baxter and Maria Straits. So, so the thing that we looked at first, and I think that's kind of like easy to sort of see because of our backgrounds, is like, what if you now have like new light particles that are coupled to the material in the star? So for example, I don't know what your favorite new light degree of freedom is, but for a lot of people, it could be an axion or a hidden photon. So that's what we started to consider first. I'm going to later mention very briefly some other scenarios that essentially actually work in the same way. So that's a scenario of large extra dimensions in which you have like Kaluza-Klein modes of the graviton and a changed neutrino magnetic moment in models of beyond the standard model physics, which then leads to enhanced neutrino emission. So these new light particles couple to the material of the star, but not very strongly. So once they're produced, they might just free stream out of the star, just like neutrinos do already. So let's consider these three scenarios. So when we were kind of first studying this, that was when the whole sort of commotion about the xenon 1 ton axis also happened. So that was a natural thing for us to look at first as well. So this is where you have like an axion which couples to electrons via this kind of coupling. And what I'm going to use later is this alpha 26 parameter, just because it's easier to work with and consistent with some of the literature. Then sort of the normal, if you will, kind of type of coupling between the Stern-Simons coupling between an axion and a standard model photon, where I here define sort of G10, which is another kind of dimensionless coupling that's easy to work with, and then a hidden photon. So just sort of a new gauge field which mixes with the standard model photon, but also has like where this gauge field has like some sort of soft mass. Okay. So, I mean, luckily, we're not the first one to consider, effects due to electrophilic axions, so axions that couple to electrons in the cores of stars or in plasmas. And so the processes to look at are semi-Compton scattering, where you have like so it's Compton scattering, where instead of a photon, you have an axion in the final state, and Bremsstrahlung, where you have like an axion radiating off the final states. So these are processes that like we thought initially could be important. It's important sort of especially to look at like semi-Compton scattering might be suppressed if the electrons are too degenerate. So there's this like degeneracy factor in here, which I computed here. So this is kind of the plane that we've been looking at all along, where you see here the core temperature and the core density. Now, I've not shown you a track, but typically our tracks start off at around 10 to the 8 Kelvin, and then about 10 to the 2 grams per centimeter cubed, and like sort of move here. And they're so well into this kind of regime where the electrons are not degenerate and this rate is not suppressed. So because it's not suppressed, semi-Compton scattering dominates in our case over Bremsstrahlung. Then for photophilic axions, you've got the Primakov effect that you might be very familiar with. So yeah, I mean, I'm giving you here like a kind of a rate. It's probably, just sort of look at this rate probably doesn't tell you a whole lot. But one thing that I wanted to point out, and that will be kind of important going on, later on is kind of the scaling with temperature. So I'm going to just compare these 3 different candidates and then they're scaling with temperature. And this one in particular scales pretty strongly with temperature. And then hidden photons, like that works like differently again. So, hidden photons may be produced in the plasma. In our regime that we're looking at, which is the regime where these like things are very light, this production is dominated by the longitudinal modes, and it scales with temperature, but not very strongly. So, here is kind of these 3 candidates and their interactions with the standard model physics compared in this plane that I've been looking at all along. And here, what I have done here is to guide your eye, showing you an example track of a progenitor which has 55 solar masses, and I've sort of followed this all the way to helium depletion. So what I'm showing you here are the central losses, and the central losses like during this kind of stage. And here in the orange line also, I'm showing you the ratio of the central losses due to these new particles over the neutrino losses. So above these lines, in each of these plots, so above these lines, neutrino losses dominate, and therefore this is probably not expected to be important. But below these lines, these new losses dominate, and therefore are more important than neutrino losses. So one thing so to notice immediately is that this electrophilic axion has like a scaling with temperature, which is very strong. So like during this process, like at the beginning of helium burning towards the end of helium burning, like you evolve through different decades of this loss, whereas for the hidden photon, it's not so strong at all. And this loss is only kind of proportional to temperature. And so therefore, like during helium burning, this loss doesn't evolve a whole lot.
Can I ask a question?
Yeah, of course.
Can you explain a little bit why this temperature scaling behavior, like electron fading is T to 6 and photon fading T to 4 and hidden photon is T?
I was going to ask the same thing. The hidden photon is the only one that makes sense to me.
That makes sense to you?
Because it's a dimensionless coupling, right? So, but anyway, yeah, I think I have the same question.
Okay, yeah, I mean, these are very different processes, right? So I don't know if it's like easy to kind of make that intuitive. Yeah.
Yeah, I think it's fine. It's fine. If there's no intuitive understanding, it's also fine.
I mean, very naively, maybe you could just say what's wrong with the most naive guess, because, for example, the electrophilic one, it's a dimension 5 operator.
Yeah. Right.
So it would have some inverse mass coupling, and so very naively you would say the rate should go like 1 over that mass squared, and therefore go like T cubed, right? But that's not what you have. So can you say like what's wrong with that very simple estimate?
Yeah, I think you need to fold in an electron density as well, or like yeah, so I think that's probably related to that. So I haven't thought about this in a little while, but
because they're not relativistic, so the densities are not just given by powers of T, right?
Yeah, that's correct.
So I guess somehow I guess that's it.
Yeah. Yeah, so I haven't thought about this in a little while. Like I can probably, yeah, but your guess is as good as mine at this point. All I can say is like this is kind of like something. It's not something that like we've checked this like against the literature and ourselves. I just don't know if I can now give like an intuitive understanding of this scaling at the moment.
Okay.
But I think it has to do with folding in the electron density, and then for this Primakov effect, folding in these ion densities. But I would have to sort of like go through the derivation again to make sure I understand the scaling with temperature in that sense. Yeah. So these are kind of well known and like written about in the literature. So I'm confident that we didn't screw up something to get like a weird scaling, but I just can't tell you now like what the scaling exactly comes from. Yeah. So, okay, so the scaling is important because the evolution during helium burning will go through different cycles of different scaling. And then the nuclear processes that are going on during helium burning also depend on temperature. So let me just start with the results. So we did the same thing. We evolved sort of stars through the helium burning and carbon burning stages of their lifetime, and through pulsations when they happened. In the cases where the BSM coupling was dialed to 0, so I had the standard model case as before, and where do you have these extra losses? And what we find is that it's actually very important, and that's something that we didn't actually have an intuitive understanding for first, but I'm going to explain to you what we found out just sort of by having a look under the hood. So what I'm showing you here is like the sort of mass versus temperature of a particular star, where like you kind of start the evolution here, and I've kind of had to make this a little bit bigger because everything's very condensed here. And so I'm comparing the gray line is kind of the standard model case where effectively this coupling is 0, and the other lines are coupling like a non-zero. And what we see is that sort of the loss during the first cycle, the loss due to winds is a lot less, or sorry, is a bit less. But what is especially important is this pulsation loss. So when you kind of go, evolve to the pulsations, you see that here for the standard model case, the pulsation loss is about 20 solar masses, so huge. Whereas for these other cases, the loss during pulsations is way less. So what's going on? So I just showed you 3 different examples. Sorry, someone's knocking on my door. Hello? Okay, thank you. Okay, sorry, there's someone knocking on my door. It's very annoying. So what you see here is that like I'm showing you a plot where on the x-axis I have this new physics coupling, which I'm dialing up from the standard model case to where this new physics coupling is large. And in the top panel shows you the time that it takes to reach helium depletion from the time that I've started, like the 0H helium branch. And you see that like if I dial up this new physics losses, this time that it takes to burn through all of my helium is decreased. And that has direct implications for how much oxygen is produced and how much carbon is produced. Because what I was telling you is there are these nuclear processes that the star is kind of burning through its helium with. And these also depend on temperature, and they depend on how long it takes to reach helium depletion. And so what you see here is that like if I dial up the new physics losses, this ratio C to O, carbon to oxygen, at the end of helium burning, helium depletion is much larger. Now that then has direct implications for the black hole mass gap, and that's been understood before, just not in the context of new physics. So this is kind of another sort of plot that's from the same paper that I referenced before, which kind of shows you, how instability supernovae work, and from like sort of going up from the bottom to the top, what's increased is the carbon to oxygen ratio at helium depletion. And what you see is that if the ratio of carbon to oxygen is large enough, so you don't have as much oxygen in the core, you might actually skip this step of like explosive oxygen burning altogether. And so for us, larger stars with new physics losses, larger stars might skip this step altogether and undergo core collapse than in the case of where the new physics losses are dialed to 0. So we have enhanced losses, which means a greater progenitus collapse, and that means that there are larger black holes. Okay, so here's this kind of on a plot. So, I mean, this was from a paper before the O3 data. So there was only kind of this very small looking set of, gravitational wave events and like derived black hole masses. And here what I'm showing you is like for all of these different values of the new physics coupling, whole grids of stars that have evolved from 0H helium branch to, you know, the very end of this cycle when everything is kind of like, when the pulsations have finished and I find my final black hole. What you see is that, like, dialing up this coupling, I indeed find larger black holes. So, okay, I wanted to sort of, we did this analysis first for, in light of xenon 1 ton. So xenon 1 ton looks at axions produced in the sun, so they're necessarily quite light, and so the xenon 1 ton collaboration explained their results, among other things, with a new physics coupling of, in this language of like alpha 26, 72 was their best fit value. So as you can see, like this, this is relevant for that explanation of the xenon 1 ton axis. So, okay, sorry. What I also wanted to say is that, like, okay, there have been lots of other studies since this xenon 1 ton axis considers like light axions because they're produced in the sun. Other stellar probes are important too, such as, for example, the red giant, the tip of the red giant branch. And so these actually are in very strong tension with this explanation for xenon 1 ton. Now, what I said before is that, like, our stellar cores are actually hotter than red giants. And therefore, this could also apply for heavier particles than are probed by red giants. But these couldn't explain the xenon 1 ton excess. Okay, so this is like for the photophilic axion. So what's actually kind of interesting here is that, like, you see I am dialing up my coupling, I'm varying it between 1 and 5. Now, here's the hidden photon. I'm still kind of like, this is still a factor of 5, but you see that the difference in like final black hole masses is much larger. And this is just related to the scaling with temperature during helium burning of this coupling. So here, basically, because the losses don't change so much during helium burning, this result just depends on kind of the absolute value, the value of the coupling. Whereas here, the scaling means that, like, it doesn't scale like quite as strongly with the coupling that with the losses going in. Okay, so here's kind of that information, just kind of that information taken from these plots, and just kind of resulting black hole mass gap. So just kind of the exact same information superimposing on this sort of final black hole mass plots. And what you see is that, like, you know, the black hole mass gap in all these scenarios with these extra losses shifts upwards. And what I haven't shown you, but we've done as well, is like the upper edge of the black hole mass gap shifts as well. So this is just kind of like you take the black hole mass gap and you shift it upwards, and quite how much you shift it upwards also depends on, like, the coupling, of course, and then also how the new losses scale with temperature. And so you see for this kind of weak scaling, like the shift is larger if you have a coupling that allows for these losses. Okay, so one interesting thing to study that we're actually looking at the moment, and I'm excited about, but it's just a bit harder to do than what we've done before, is that, like, if you have like a heavier degrees of freedom which couple, you know, with a particular coupling to the stuff in the star, they might actually also kind of just actually form some sort of a thermal population, or they might like form a population that does kind of in a sense the same thing as that electron positron pairs do. And so they might, for example, lead to like a new instability region, which, you know, when these new degrees of freedom are produced, they will destabilize the star. So just sort of as an example, not that like we have particular models in mind for these particular benchmarks, I'm showing you different masses. So this is for a, let's say I have a bosonic new particle, and then that has a mass of an electron, you see that this region is slightly different than I found for the electron, but that's because these just have slightly different statistics. And I'm showing you sort of what if this particle has 10 times the mass of the electron and the electron mass over 20. You could potentially find, if you have a coupling large enough to allow for the equilibrium, an equilibrium to be formed during helium burning, you might find like a new instability due to this new particle. Now you might say, okay, well, these new particles, they're relatively well probed by lots of other things that we've tried. And that's true, but one saving grace is that helium burning, I don't know if you remember from that plot that I showed you before, takes a long time. So that takes like about 10 to the 5 years. And so so you might live with like small couplings, as I'm showing you an estimate for here.
Sorry, can I ask a naive question? Maybe should have asked a little bit before, but so these objects are pretty hot, right? I mean, you said close to an MeV, so they're hotter than what I'm used to. I'm not an expert, but hearing about like for like supernova 1987, those kinds of supernovas, they're more like keV. Yes.
Yeah, so actually I think supernova, like just in the explosion itself, they might reach actually very hot temperatures, like for their cores. I don't have a, I think yeah, sorry.
Right. So because those of course give stringent constraints on axions from requiring that there's not too much emission. So obviously you would tell us if these are probing a region that's allowed by these supernova constraints that you're talking about, yes? And so I'm just wondering, should I think of this effects that you're talking about as more sensitive to these kinds of things like axions and so on? I mean, the observations are a little less clear, right? So there's some more, something's a little more less obvious there, but basically you are sensitive, these effects that you're talking about are sensitive to larger values of F axion, for example, compared to supernova cooling constraints. Is that correct?
Yeah, no, good question. So I, like, both Sam and myself actually have written supernova 1987A papers, and
yes.
I think the answer is like slightly model dependent, but taking like the example of an axion that you mentioned. So for example, someone asked us, this effect that we've been describing, like of like an axion like particle coupling to photons with a certain Simons coupling. Could you also probe QCD axions that way? And so the answer in that case is that, like, so just taking that coupling at face value, right? So this like the coupling of axions and between axions and photons, just this type of coupling. Right. Oh, sorry, this type of coupling.
Yeah, that one.
So then we are more sensitive than supernova 1987A. But for QCD axion also couples to nucleons like protons. And so in that case, that sort of coupling to protons leads to like the supernova constraint being stronger, just because like you necessarily don't live with just this coupling, but also coupling to protons in that case. But typically just taking sort of the models, just having the standard model and only adding these couplings, in that case, this is a more sensitive effect, smaller couplings, typically. Yeah.
Okay.
So.
Thank you.
Okay. Yeah. Yeah. So okay, so this is actually still kind of work in progress, and the reason is that, like, as you might be able to imagine, it's actually a bit harder to modify just the equation of state of a star than it is to just like add an extra loss to a dynamical code. So this is something we're currently working on, seeing if I have now a particle which is like heavy enough to actually form some population in the star, so masses that are like round about the electron mass, if that could affect this whole story. And it's actually kind of hard to guess before you, I think this is a kind of a good example of how hard it is to guess what happens before you've actually done a detailed simulation. Because we were talking about this with like a few of these astrophysicists that have like studied para-instability supernovae for a long time. And yeah, if there's like, let's say I have this new instability region, which is like slightly shifted from this old one, but now I'm looking at particles that don't actually, have such a strong coupling like electron-positron pairs, such that like immediately after this collapse, you might form this kind of, you might sort of create these again. So perhaps you only have like kind of one pulsation, and then what happens from there, it's kind of pretty hard to predict. It also depends on like if it's at the end of helium burning or during helium burning. So this is something that we really kind of just have to simulate and then kind of look under the hood to see what happens. But yeah, we're interested in. So here's kind of a motivation for why we'd be interested in that. We're hoping that you could probe this heavy parameter space in that way. So this is kind of like for the example of the hidden photon. I've shown you sort of to guide your eye, like about like what sort of masses like 10 to the 8 Kelvin corresponds to, and 10 to the 7 Kelvin. So we are like kind of living in this region with like because our stars are much hotter, where you live, you could probe potentially like larger masses. So that's what we're currently looking at. Okay, so one thing that like, I mean, I noticed that I'm kind of like almost at the end, but like one thing that I just kind of wanted to mention is I have been talking mostly about extra losses. So collaborators of mine have sort of discovered another type of scenario, which is which works a bit differently, which is like in a modified gravity model. Like imagine that you have like some sort of theory of modified gravity, such that locally in the course of these population 3 stars, I had a different effective like Newton's constants. So then what happens is this is affected in a different way. Basically, what you might think about is like, okay, let's say I'm making gravity effectively weaker, then it's like I'm evolving a larger mass black hole, and the other way around. So because of that, like a decreased local strength of gravity means that you can produce heavier black holes. Whereas if you lift with like an increased local strength of gravity, that means like you'll find lighter black holes. Okay, so here's kind of like, when this GW 1905-21 like was released, of course, like because this is something we've been working on for a few months, we were too excited not to sort of comment on it. So we kind of looked at all of the different models that the models that I've talked about with you, and then these other 2 models that essentially work in a similar way and modify gravity, just to see, for this amazing like and strange event, like quite how big the couplings have to be to explain it. And we find is that like it's actually still quite hard to explain it. Yeah, here are the couplings. So some of these models in particular, for example, the neutrino magnetic moment model, where you modify the anomalous magnetic moment of the neutrino, you have to modify it by so much to actually get near explaining these events that that this has kind of been long excluded. And for most of these models, it's in some tension with some other probe, but most of the other probes depend in a different way on mass, so it's kind of hard to plot in the same plots. So I should say also that like for each of these like ticks, is a whole grid of like simulations of stars. So it's like so many GPUs or CPUs went into this plot. But it's kind of interesting to see that like maybe, this like new physics models, like the ones I've been considering, at least help a little bit explaining, these masses that were found. So looking ahead, so I know that I've mentioned that like the 03 data set has been released very recently. So that's only part of the 03 data set. The rest will be released next year. And so I mean, I don't know if you remember when I showed you the O2 and O1 data, and then I flipped to the O3 data, and that's like a large increase in how many events there were. And so likewise, I think with the next observation runs of LIGO and Virgo, but also as new detectors are being added to the network, and even third generation experiments like the Einstein telescope and Cosmic Explorer, we'll just have a lot more information. We'll just have so many black hole merger events. So we will actually be able to do black hole population studies. And these are plots from an early paper. So back in the time when we had only 4 binary black hole mergers, only a few years ago. And they kind of already, Maya Fishback and Daniel Holtz were already kind of looked at, what you could how you could study the black hole mass gap using these events. And so just using sort of Bayesian studies, like you can see here, this is kind of their posterior on the edge of the black hole mass gap. That's definitely not so constraining as what you can do now, but hopefully, we'll be able to do with the large population of like mergers that we will have, we'll be able to do black hole population studies, and we will actually know, quite well, like where the edge of the mass gap lies. Okay, so this kind of concludes what I wanted to tell you at this point, at least. I am personally very excited about gravitational waves generally. I think they're a very cool new opportunity to study questions in astrophysics and cosmology, but also, have applications in particle physics, and that's what I study. So today I talked about binary mergers, and I've argued that they allow for black hole population studies. And it's in particular very interesting because there's kind of this cool astrophysical effect takes place in the centers of massive stars, which leads to a black hole mass gap. So a very prominent feature in these black hole populations. And I've shown you that that's also interesting for a particle physicist, because the very high temperatures in the cores of these stars lead to processes being important that we have thus far not have had any other probes of, and therefore for the black hole mass gap can be used to probe new physics. So I've kind of given the particular example of this very recent event, GW 190521, which is an interesting puzzle, which people are trying to explain from all sides. So I've offered you kind of a bit of an alternative explanation to some of the other dynamical explanations that exist. And perhaps beyond the center model physics can play a role in partially explaining this event. Thank you very much.
Great, thank you. If there are questions, people should just speak up. I'm not competent to organize this, so please just, any questions?
Actually, I have a question.
Mm-hmm.
So do you expect the self-interaction for this axion like a particle will affect your calculation?
Self-interaction.
Yeah.
So, I mean, axions are very, very small self-interactions, right? Because typically that goes like m squared over f squared. But let's imagine that they had large self-interactions. I think what's more important is I guess if you so one assumption that we've made is that these things are produced and they couple quite weakly to all of the other stuff in the star, so they will just free stream out of the star and not rescatter. So yeah, if the self-interaction might play a role in if you calculate kind of a thermal population forming in the star. But I think what's more important is the interaction with the other stuff that's already present in the star. So I think what we have been studying so far is not affected by self-interaction. But what we are studying later on, where we're kind of studying the equation of states, that will be affected by a significant self-interaction. But then I should say there's no reason that in particular axions to think that they have a large self-interaction.
Okay, thank you.
Other questions? I mean, I have another question. So I think I didn't really understand. I think I understood that a part of this is the basic reason why this additional energy loss is giving you bigger black holes is that it is kind of it's short-circuiting this explosion, that this pair production instability that gives rise to this explosion. That's
Yeah,
what's
not
normally
quite, actually.
responsible to the mass gap. Did I understand that part right?
Not quite, I think.
No?
So what's
Sorry.
happening is just, yeah. So what's happening is just that, like, before you even get to the explosion, you just produce less oxygen. So the explosion is fueled by oxygen sitting in the core. And so if you have less oxygen, the explosion itself is less.
I see. Okay,
yeah.
so thank you. So so then my next question is then, but when you sort of shown that you say it's difficult to explain with new physics, so you're not able to give me some model where you can just be way into this mass gap. And I didn't really understand, well, what's stopping you? Is it just other constraints? Are those models ruled out by other constraints?
It's
Or
just
is it some astrophysical thing or what?
It's just other constraints, like so yeah. So so I don't know if there is a particular model which like would lead to sort of emission during this helium burning process, right? So like would lead to extra losses during helium burning, which would not affect, for example, the tip of the red giant branch.
Yeah.
So if you have a model in which, for some reason, you know, these losses are on for my process and not on for other stellar cooling processes, then that model, you know, could explain this event. But for us, we are kind of limited by that. We also kind of take into account existing constraints. And so, for example, for you know, people have also looked into these large extra dimension models in the context of like stellar evolution, but these are probed, for example, at colliders. So what I've showed you, for example, here is like, you know, extra dimensions with like 2 extra dimensions. This is with like a fundamental scale, you know, at like a few TeV, but colliders already, you know, kind of constrain this like to a few TeV. Okay. So yeah.
Okay, thanks. All right, any other questions? Okay, well, let's thank Djuna again, and let's stick around. Anybody who would like to stick around and talk, please feel welcome to do so. So I don't know if you can unmute and clap. I think that would be nice.